Okay. So, let us continue the discussion on axial turbine. So, we are looking at the different stage efficiency and their estimation, and we have looked at the TS diagram and the different losses, and this is where we stopped that with an argument that lambda could be equals to y. Now, how we can do that? We can look at this y n, which is p naught 1 minus p naught 2, and this is the ratio. So, one can write that p naught 1 by p naught 2 minus 1 divided by 1 by p 2 by p naught 2, and p naught 1 by p naught 2 is p naught 1 by p 2 into p 2 by p naught 2. So, that is T naught 1 by T 2, which is gamma by gamma minus 1, and T 2 by T naught 2, which is gamma by gamma minus 1. But T naught 2 is T naught 1, since P naught 1 and P naught 2 is T 2 by T 2 prime, gamma by gamma minus 1, then we can write y n is T 2 by T 2 prime minus 1 by T 2 by T naught 2 gamma minus 1. So, which would be 1 plus T 2 minus prime, which is gamma by gamma minus 1 minus 1, and 1 minus T 2 minus T naught 2 by T naught 2 plus 1, which is gamma minus 1. Now, one can give an argument T 2 minus T naught prime is smaller than T naught prime, and T 2 minus T naught 2, which is smaller than T naught 2. So, if that is the case, then the term which are there inside the bracket can be expanded using binomial expansion, and we can write like y n equals to T 2 minus T naught prime by T 2 T naught 2 minus T 2 T naught 2 by T 2 prime. So, this is equals to lambda n T 2 by T naught 2 by T 2 prime, which is lambda n T naught 2 by T 2. Okay. So, this is, although this approximation is not very accurate, but fair enough to use, and we have T naught 2 by T 2 is 1 plus gamma minus 1 by 2 m 2 square. So, even at 2 where m 2 equals to 1, lambda n is roughly 0.86 y. So, they are, that is why the comment is that they are quite close enough values. Now, this lambda n and lambda r, they can be also correlated to the isentropic efficiency of the stage eta s. Now, how do you know eta s is T naught 1 minus T naught 3, T naught 1 minus T naught 3 prime. So, this is 1 by 1 plus T naught 3 minus T naught 3 prime by T naught 1 minus T naught 3. Okay. So, and what we can write from the TS diagram, that T naught 3 minus T naught 3 prime is T 3 minus T 3 prime, which is T 3 minus T 3 prime plus T 3 double prime minus T 3 prime. So, this we can write from the TS diagram. Now, what we have, that T 2 prime by T 3 prime is T 2 by T 3 double prime, since because they are equal to P 2 by P 3 gamma minus 1 by gamma. Okay. So, we can further simplify the terms, like T 3 prime minus this by T 3 prime, T 2 minus T 2 prime by T 2 prime, then T 3 double prime minus T 3 prime, which would be equals to T 2 minus T 2 prime, T 3 by T 2. Since T 3 prime by T 2 prime is T 3 by T 2, we will write eta s is 1 by 1 plus T 3 minus T 3 double prime plus T 3 by T 2, T 2 minus prime divided by T naught 1 minus T naught 3. Okay. So, this further we can do 1 plus lambda r W 3 square by 2 C p, T 3 by T 2 lambda n V 2 square by 2 C p, T naught 1 minus T naught 3. So, if you look at all these relationship that we are writing down here, they are coming from the TS diagram. Now, what else we have? W 3 is V z sec beta beta 3, V 2 equals to V z sec alpha 2, and delta T theta T naught s is T naught 1 minus T naught 3, which is u V z by C p tan beta 3 plus tan beta 2. So, which u V z by C p tan beta 3 plus tan alpha 2 minus 1 by phi. So, we can rewrite this expression of eta s, which is going to be 1 phi by 2 lambda r sec square beta 3 T 3 by T 2 lambda n sec square alpha 2 tan beta 3 minus 1 by phi. Now, since y is lambda, then y r and lambda y n may replace lambda r and lambda n in this equation. Okay. So, then we can replace these things and get the stage efficiency and all this. So, the next what we will look at the mean radius stage design. Okay. So, mean radius stage design. So, from cycle calculations we have already got the following parameters, that m dot eta t t naught 1 delta t naught s p naught 1 by p naught 3 and p naught 1. Now, n is the rotational speed or RPM, mean blade speed is u. So, that is mean blade speed, and this mean blade speed is restricted by the rotational stress criteria and they have to be satisfied, and also we assume some value of lambda n, let us say 0.5, which is a reasonable guess, and also we start with an assumption Vz2 is Vz3 and V1 would be V3. Okay. So, then we write this 2 Cp delta T naught S by U square. Now, we choose a value of phi, and using that what we can calculate the degree of reaction. Now, since psi is 2 phi tan beta 2 plus beta 3 and tan alpha 2 is tan beta 2 plus 1 by phi and alpha 3 is 1 by phi. Now, if we consider a single stage turbine and we have Vz1 equals to Vz3, right. So, it has to be single stage and the inlet is axial. So, alpha 1 is 0 and V1 equals to V3. So, which means alpha 1 0, alpha 3 also 0. So, that gives us tan beta 3 is 1 by phi and tan beta 3 is 1 by 2 phi psi by 2 plus 2 degree reaction. So, here we get half of 2 phi tan beta 3 minus psi by 2. Now, so this guy, the degrees of reaction that increases from root to tip, therefore, small values of this degree of reaction at mean radius must be avoided, because that will mean negative degree of reaction at the root. Again, we have tan beta 2, which is 2 phi minus tan beta 3 and tan alpha 2 is tan beta 2 plus 1 by phi. So, next we can calculate the density as station 1, 2 and 3. So, let us draw the velocity triangle. So, this is u, W3, V3, So, this is W3 V3 W2 V2. So, this is alpha 3, beta 3, beta 2, alpha 2, H is blade height. Now, what we write here, Vz2 is u Vz by u u phi, and V2 equals to Vz sec alpha 2. So, T naught 2 minus T 2 equals to V2 square by 2 Cp. Since T naught 2 equals to T naught 1, which is T 2, so equals to T naught 2 minus V2 square by 2 Cp. And what we have, T 2 minus T 2 prime is lambda n V2 square by 2 Cp. So, we get T 2 prime is T 2 minus lambda n V2 square by 2 Cp. Also, we have P naught 1 by P 2, T naught 1 by T 2 prime, gamma by gamma minus 1. So, which gives us P 2 equals to P naught 1 T naught 1 by T 2 prime, gamma by gamma minus 1. So, rho 2 is P 2 by T 2. So, that is how we get the density. Now, from the area A 2, which is m dot by rho 2 Vz 2. So, this is an annulus area at plane 2. So, the A 2 n would be A 2 cos alpha 2. So, this guy is not because it is not a repeating stage, we are assuming that V 1 is axial, and this together with the assumption the other assumption that we have made here. So, at 1 or Vz1 is V1, which is V3. So, we get T naught 1 equals minus T 1 is V1 square by 2 Cp, from where we get T naught 1 minus V1 square by 2 Cp. And the relationship of P 1 by P naught 1, which is T 1 by T naught 1, and density we get P by R T 1, and area rho 1 V z 1. Similarly, at 3 we get T naught 3 equals to T naught 1 minus delta T naught s, and T 3 equals to T naught 3 minus V 3 square by 2 Cp. So, P naught 3 is now we use the relationship of P 3 equals to P naught 3 T 3 by gamma minus 1, and rho 3 is P 3 by R T 3. So, we get A 3 Vz3. Now, is 2 pi n Rm. So, we get Rm equals to by 2 pi n. So, that is at the mean radius, that is what we can get. So, area would be 2 pi Rmh, which is h by n, and h equals to a n by So, the root radius is Rm plus h by 2, and a tip radius and root radius is Rm minus h by 2. Now, all A1, A2, A3 all are calculated. So, note that all the relationship we have derived well for Vz2 equals to Vz3. If Vz2 is not equal to Vz3, then u by Vz2 equals to tan alpha 2 minus tan beta 2, and u by Vz3 is tan beta 3 minus tan alpha 3, and psi equals to 2 Cp delta T naught s by u square 2 by u 2 tan alpha 2 3 tan alpha 3. Okay. So, also in the flare is not symmetrical. So, u must be replaced by um2 and um3. For this preliminary design, we have taken losses into account via lambda n and eta s rather than lambda r or lambda n. So, lambda n is implied by the design, and lambda r can now be calculated. So, we get T2 by T3 prime equals to P2 by P3 gamma minus 1. So, which means T2 P2 by P3 gamma minus 1 by gamma. So, for this preliminary design, we have taken losses account via n and eta s rather than lambda r and this. Now, W3 is Vz3 by cos beta 3, and lambda r would be T3 minus this by 2 Cp. Typically, lambda r is greater than lambda n due to tip leakage loss in the rotor blades. Okay. So, this is how we get this done. Now, the next is the vortex theory. Okay. So, what is that? This is the next step in the design. So, to consider the 3D nature of the flow so far as it affects the variation of the gas angles with radius. So, this is to consider 3D nature of the flow. Second, to consider the blade shapes. and that is also necessary to achieve the required gas angles and the effect of the centrifugal and gas bending stresses on design. Third, to check the design by estimating lambda n and lambda r from the result of cascade test suitably modified to take account the or take into account the 3D flows. Okay. So, when we take the 3-dimensional effect considering radial equilibrium. So, we have already seen in compressor that u is r omega. So, u goes up as rotational speed goes as r goes up. So, to maintain a smooth flow, the blade has to be twisted. So, the twisted blade required. Second, twisted blading designed to take into account the changing gas angle, which is called the vortex blading. Okay. Now, we can do free vortex design, where stagnation enthalpy H naught is constant over the annulus, which means d H naught by dr would be 0. B, axial velocity is constant over the annulus, and C, V theta is inversely proportional to radius, or V theta r is constant. So, with this assumption, radial equilibrium condition is satisfied, and this design is called the free vortex design. Okay. Now, for nozzle, the H naught is constant at the inlet, okay. Then it will be constant at the. So, for nozzle, if H naught is constant at inlet, it is constant at outlet, because no work is done in the nozzle. Second, if we design the nozzle blade such that V Z2 is constant and V theta 2 r is constant, so this means the radial equilibrium theory is satisfied at station 2. Similarly, if rotor blades are designed in such a way that V Z3 is constant and V theta 3 into r is constant, then it also satisfied the radial equilibrium theory. So, it can be shown that H naught 3 is also constant, and hence radial equilibrium theory or radial equilibrium is satisfied at 3. Okay. So, what we write? We write from angular momentum equation. What we write? W is u delta V theta, which is known. So, we can write u V theta 2 plus V theta 3, which is omega V theta 2 r plus V theta 3 r, which is constant. Now, also W equals to C p delta H naught. So, if W is constant over R, then delta H naught is constant over R. So, hence H naught 3 is constant over R. Okay. So, which tells me that H naught must be constant at inlet and at outlet 2. So, that A is, so to maintain this, the H naught has to be constant at the inlet and at the outlet 2. So, that this condition is satisfied A. So, this is what you get when you are talking about the free vortex design. So, we will stop it here and continue this discussion of the design in the next lecture.